Hello, in this video we are going to be talking about integration by parts. Specifically, we're talking about integration by parts with definite integrals, and we're going to illustrate how to apply integration by parts with definite integrals by working through example 6, where we are asked to evaluate the integral from 0 to 1 over the square root of 2 of y arc sine of y squared dy. So, to begin with, we need to decide what we should choose for u and dv. In this problem, we can just go with our rule of thumb, ILATE, when picking our choice for u. And the first letter in ILATE stands for inverse trig, then logarithmic, then algebraic, then trig, and then last exponential. So if you recall, we pick u moving down, which means that we're going to pick u to be inverse trig first. So we do have an inverse trig function in our integrand, which means that we're going to pick u to be that inverse trig function. So the arc sine of y squared, and dv will be everything else. So that is y dy. Now we differentiate u to get du. Remember, the derivative of arc sine is 1 over the square root of 1 minus whatever the argument is. So that's y squared squared, and the chain rule says we need to multiply by 2y as the derivative of y squared. Now to get v, we're going to integrate dv, so we're going to integrate y dy. That's going to give us a 1/2 y squared. So the integral from 0 to 1 over the square root of 2 of y arc sine of y squared dy, this is going to be uv minus the integral of v du. So u times v is 1/2 y squared arc sine of y squared, and then we have minus the integral of v du, so that is 1/2 y squared times 1 over the square root of 1 minus y squared squared times 2y, and that's a dy, and I'm sorry I missed a dy when I was differentiating u. But since we are evaluating a definite integral, we need to remember that on the right side of this equation now. Our first term, the 1/2 y squared arc sine of y squared, has already been integrated, which means we just need to evaluate it. So we're going to have a vertical bar and our bounds of integration, 0 and 1 over root 2. Our second term still needs to be integrated, so we need to remember to carry our bounds of integration there. Okay, so at least for now, let me just rewrite this first term, 1/2 y squared arc sine of y squared, to be evaluated at 0 and 1 over root 2. The integral, we're going to simplify. The 1/2s cancel, like so. We are going to end up with a y cubed by combining there, and y squared squared will give us a y to the 4th. So we end up with the integral of y cubed over the square root of 1 minus y to the 4th dy, and then of course we have our bounds 0 and 1 over the square root of 2. Now for this integral that we have now, we can do a substitution. Since we're done with the u and the dv from the integration by parts, you could actually get away with using a u here for your substitution, but just to make sure that we don't confuse our u's, I'm going to go ahead and choose a w. Specifically, I'm going to let w be 1 minus y to the 4th. Then dw will be negative 4y cubed dy. And notice that we have a y cubed and a dy in our integral. So I'm just going to go ahead and divide through by the negative 4. So we get negative 1/4 dw is equal to y cubed dy. Now since we have bounds of integration, we are going to have to find new bounds with our substitution. So first off, when y is equal to 0, w is equal to 1 minus 0, or 1. When y is equal to 1 over the square root of 2, w is equal to 1 minus 1 over the square root of 2 raised to the 4th, which is going to give us a 1/4 there, so we have 3/4 as our new upper bound. Okay, now returning to the integration, we are going to have this is equal to 1/2 y squared arcsine of y squared to be evaluated at 0 and 1 over root 2. Then we'll have minus, our new bounds of integration are 1 and 3/4. We're going to have a negative 1/4 dw over the square root of w. Rewriting our first term. Then I'm going to pull the constant out of the integral, so we get plus 1/4 integral from 1 to 3/4. I'm going to rewrite the integrand as w to the negative 1/2. Oops. 1/2 dw to make it easier to evaluate that integral. Again, rewriting our first term. We'll plug in our bounds in a little bit. Rewriting our constant. When we integrate w to the negative 1/2, we will get w to the 1/2 divided by 1/2, so we're going to have a 2 there that we're multiplying by, and that gets evaluated from 1 to 3/4. So now all we have left to do for this problem is to plug in our bounds of integration, and notice that the two terms that we have, one here and one there, have different bounds of integration. So this is the easy thing to forget with integration by parts with definite integrals. This first term, which we got by applying integration by parts, this is fully integrated. You have to plug in your original bounds, no matter what else you do for the other integral. So we have two terms here, both need to have the bounds plugged in, so we will go ahead and do that. 1/2, 1 over the square root of 2 squared, arcsine of 1 over the square root of 2 squared. Then we have minus 1/2 0 squared, arcsine of 0. And this all comes from the first term in the previous line. And then we'll have a plus. 1/4 times 2 gives us a 1/2, so we'll have 1/2, and then 3/4 to the 1/2 minus 1/2 1 to the 1/2, and those two terms now come from our second term in the previous line. So, a couple of things to note here when we are simplifying. The arcsine of 1 over the square root of 2 squared is going to be the arcsine of 1/2. So this is the same thing as saying what angle gives us a sine value of 1/2. And that is going to be pi over 6. Next, the arcsine of 0 is the same thing as saying what angle gives a sine value of 0. That one's a little bit easier. That's just going to be 0. So the arcsine of 0 is equal to 0. The arcsine of 1 over root 2 squared is equal to pi over 6. So we are going to plug those values in so that we end up with, let's see, 1/4 times pi over 6 minus 0 plus, we can simplify this to the square root of 3 over 4 minus 1/2. And so we'll get our final simplified answer to be pi over 24 plus the square root of 3 over 4 minus 1/2. And that is our final answer for example 6.